In this video, we'll look at allylic halogenation, which proceeds through a radical mechanism and is very similar to the radical halogenation reaction you learned in first semester. In fact, it was the first reaction you learned. So for this reaction, we need to have an allylic position, so a position next to a double bond. We're going to look at allylic chlorination first. So we add Cl2. I'm going to go down here for the products, excuse me. So this gives me the chlorine at that allylic position again, and then plus HCl as a byproduct. So let's look at the mechanism for this reaction. The first step is an initiation step where we generate some initial chlorine radicals, and that gets the reaction going. So that chlorine bond is a longer, weaker bond. Upon some type of energy, in this case heat, I can homolytically cleave the bond to give chlorine radicals. Remember, I'm using single-headed arrows because I'm moving one electron at a time. So whenever there are radicals involved, we're going to see those single-headed arrows. Once that chlorine radical has been made, it can go interact with one of our alkenes. And it is going to take the proton off of the allylic position, the next door neighbor position to the double bond, because that gives us a resonance-stabilized intermediate. So this chlorine is going to abstract an H. That's how we make our HCl byproduct. And then I'm going to have one electron go on to the carbon adjacent to the double bond. So these two arrows here, let me change pen colors so we can look, show me that I'm making HCl. And then this last arrow here shows me that I'm making the radical. So over here I have HCl as my byproduct. And then I get this radical intermediate, but it's adjacent to a double bond, so it's resonance stabilized. So I have the electron on the outside fold in and one from the pi bond that's closer to it fold in to make a double bond on the left side. The remaining electron from the original double bond is going to go out onto the right carbon to give me that right side resonance stabilized radical. So I'm going to make these radicals a little bigger so we can see. So I have two resonance contributors for my radical intermediate, which makes it particularly stable, and that is why the proton next to the double bond is plucked off. And then finally, that radical intermediate can abstract a chlorine to make the final product. Now remember that there is a much higher concentration of Cl2 in solution than there is chlorine radicals, and so it's much more likely that this radical is going to bump into a Cl2. So these kind of meet in the middle to say that a carbon-chlorine bond is being made, and another chlorine radical is generated to go on and propagate further. So there is my allyl chloride, and then I have my chlorine radical which spit out, and that will go on to propagate and react with another alkene. So the same kind of reaction can be accomplished with bromine, but we can't use Br2. So if we use Br2, what we'll see is addition of Br2 across a double bond. There's a high concentration of Br2 at any given time, and that gives this addition reaction. And the reason that we see this with Br2 and not Cl2 is because this bromonium ion is more stable than the analogous chloronium ion. So here I have longer, weaker bonds, which allows for more distortion, and that gives me a less strained intermediate. And so because this is more stable, this reaction will go through addition of bromine across a double bond. Instead of allylic halogenation, because there is a high concentration of Br2 in that solution. Whereas with the chlorine, this intermediate is a little bit less stable, and so radical halogenation, that allylic halogenation, is the lower energy pathway. In order to accomplish allylic bromination, we just need to use a different reagent. And this guy is called N-bromosuccinimide, or NBS. So I'm going to draw him so you can see. So that's what it looks like. N-bromosuccinimide, which we call NBS. So what this does is it just provides a small concentration of Br2 for the reaction, and without a large excess, we don't see addition across the double bond, we see allylic halogenation. So this provides a low concentration of Br2, which favors allylic bromination over that addition reaction. So if we want to add Br2 across a double bond, we can just add Br2. If we want to put a bromine at the allylic position on a system, then we need to use NBS, which allows us to generate just a small amount of Br2 in solution at any given time, favoring that allylic bromination pathway. So as an example, I could use cyclohexene and put it in solution with NBS, heat it, and then I'd use carbon tet, which is just a solvent. And we need to be able to identify these allylic positions, so anything next door to a double bond is an allylic position. In this case, the allylic positions are identical to one another. If I had different types of allylic positions, then I would see different products. Let me change back to blue here. So now my product will be the bromine at that allylic position, and I don't need to worry about any kind of competition from Br2 adding across the double bond. And then what ends up happening to the NBS is it ends up swapping out an H for a Br. So this is just our byproduct of the reaction that comes from the NBS. So we're not going to do the whole mechanism for the NBS because it's a little bit more complicated, but it does proceed through a radical mechanism. And there are alkyl radical intermediates. And so, as we've talked about before, a tertiary radical is more stable than a secondary radical, than a primary radical, than a methyl radical. So radicals are much the same as carbons that have positive charges, and that the more substituted a radical, the more stable the intermediate. That will give the lower energy pathway, and so you would see, if there was a choice, a major product that was more substituted than one that was less substituted. So say we use that same system, but this time I'm going to put a methyl group next door. Now I have two different types of allylic positions. So I have 1 and 2 there. So if I put in solution NBS, heat, and my solvent, what I'm going to see is mostly substitution at the more substituted tertiary system, right? So this is a tertiary carbon, that's a secondary carbon. And then I might also see a little bit of substitution at the secondary system. And the reason that the majority that I see is this tertiary system is because this is the most stable intermediate. Its resonance stabilizing is at a tertiary carbon.